Okay, in this video I want to talk about the relationship between instantaneous velocity and acceleration, and between instantaneous velocity and position. So let's say we had a situation where we had a car where its initial position in a coordinate system was 0 meters. X naught is equal to 0 meters. We don't really need a y coordinate for this problem. There would just be a requirement for x as a function of t. And let's say that the initial velocity was 3 meters per second, and the acceleration was constant and equal to 1 meter per second per second. So starting with v versus t in the middle here, I'm going to make a v versus t plot now of velocity on the vertical axis versus time on the horizontal axis. Time is in seconds, velocity is in meters per second. And so with the given information, Vx of t is v naught x plus ax times t. That's one of the kinematic equations for constant acceleration. And so plugging in the assumed values, that equates to 3 meters per second plus 1 meter per second times t. So first of all, let's go from v versus t to a versus t. So to get from v versus t to a versus t, we simply take the derivative of this expression here, 3 plus 1t. The derivative of 3 it's a constant, so that's 0. The derivative of 1t is 1. And so from calculus, the acceleration is constant and equal to 1 meter per second per second. Geometrically, the derivative is the acceleration is the slope of the v versus t curve, and since we have a straight line, that slope is constant. And so in a different way, we arrive at the same answer of the slope of the v versus t curve is 1 meter per second per second. Up 1 meter per second over 1 second is 1 meter per second squared. Up 1 over 1, constant slope there. Now let's go the other direction. Let's go from instantaneous velocity to position. And so the calculus relationship is integration. And so we can take the v versus t expression, which for constant acceleration is v naught x plus ax times t, and integrate from 0 to t. The x of t is going to be the initial x position plus this integral. And since we're assuming that this is 0, all we have left as we go over to the other side of the equal sign here is simply the integration from 0 to t of this straight line, and what we get is integral of v naught x is v naught x times t, and the integral of ax t is 1/2 ax t squared. So if we plug the values in, that's 3 meters per second times t plus 1/2 times 1 meter per second times t squared. So we have a x versus t here, which I have not plotted. I will let you do that. The tabular values are over here, and typically what I do in problems like this is I put this function into my function screen on my calculator and set it to tabular mode, and just read the values off from my calculator and put them into the table here. And so what one would get here is a quadratic based on this being a t squared highest degree for x of t. So here's some questions for you. For this particular scenario, with the values that we've assumed here, what is the velocity at t equals 10 seconds? What is the displacement from t equals 5 to t equals 10? There's a couple of different ways of doing this second one. Number 3, what is the position at t equals 10? Question 4, when was v of t equal to 0 meters per second? And so what I'm asking you to do is to extrapolate the performance backwards in time, assuming that it continues to do the same thing. Was means that t is going to be less than 0. Finally, what is the acceleration when v of t is equal to 0 meters per second?